Hello everyone, welcome to lecture 18 on Mechanics and Materials 1. This is our third lecture on the topic bending, and today we want to cover sections 6.3 and 6.4 of the chapter 6 of the Hibbeler book. In total we have 4 lectures on the topic bending, and after this we have a fourth part to that, which would be lecture 19. So what we want to do is to formulate the bending deformation for a straight member. But before I do that, I would like to remind you of what we have done for similar problems in the past when we dealt with axial loading and when we dealt with a torsion problem. So if you think of axial loading, we had a beam, a straight beam again, on top of which you have applied a normal force P. For this type of application, if you think of the loading that we applied, it was a force, it was a normal force, more specifically, and the type of stress-strain response or stress-strain developed in the material was normal stress and strain. Also, you may remember that for this problem, stress was calculated as P divided by A being the cross-sectional area, and for instance, delta was calculated as PL over EA. Delta was the deformation or change of length of the straight member or the beam. After that, we talked about torsion. For torsion, we apply a torque as opposed to a force. So you have a torque, and torque is basically a moment, but it's also a normal moment. Normal in the sense that its direction is as shown in the picture, so it will cause a twist of the member. Now for this problem, stress and strain were not normal anymore, they were shear stress and shear strain. And if you remember, for tau, for shear stress, we calculated the relation TR over J, J being the polar moment of inertia, which again, it should be compared with the relation we had as P over A for axial loading. And then instead of delta equals PL over EA, for a torsion problem, we had phi equals TL over GJ. So there were similarities and differences between the two problems, but what happens now is that we want to talk about the bending problem. So bending problem is very interesting in the sense that they apply the loading that we apply on the member is a moment. The loading is a moment, but in contrast to a torsion problem, it's a tangential moment. It's not a normal moment. So the type of loading that you apply is not a force, which makes it different from the axial loading, but the type of stress and strains that are developed in this bending problem inside the member, they are normal stress and normal strain. So you can see that at the stress strain level, the bending problem resembles a, let's say, an axial loading problem, and at the loading level, it's more similar to a torsion problem. So now we want to discuss this. We want to formulate the deformation of a straight member, and then again, the fact that it's a straight member, it's not a surprise. We also dealt with mainly with straight members when we talked about axial loading and when we talked about torsion. So what we want to do now is to analyze the bending deformation of a structure like this. And as I mentioned, the first assumption is that it must be straight. The second assumption is that we assume it's a prismatic beam. So prismatic in the sense that it must have identical cross sections. So what does that mean? That means we are not talking about the bending of a member which looks like this, because it's not straight. So this is not straight. That's not acceptable. We are not talking about bending the formation of something like this, because now it's not prismatic. You can imagine that at different levels you have different cross sections. So it's not prismatic, and we certainly are not talking about bending the formation of something like this, which is neither straight nor prismatic. Okay, so what we do is bending the formation for straight prismatic beams. Also, we assume that the member, the beam, it must be symmetric with respect to one axis at least. So it's symmetrical with respect to an axis. And then you apply a moment about an axis perpendicular to the axis of symmetry. This you will see in this picture. So basically, if you look at the beam here, you have an axis of symmetry, and the moment is prescribed with respect to axis Z. Let's say here y-axis is the axis of symmetry and Z is the axis with respect to which you apply the moment. So Z and Y are orthogonal to each other. So this is exactly the assumption that we just talked about. So the moment is applied about an axis perpendicular to the axis of symmetry. Also, you can see that we have symmetry with respect to at least one axis. So this is axis of symmetry. And also it's a straight prismatic beam. I also mentioned that usually for the direction of y, z, and x-axis, we follow what you see in this picture. So usually we assume that y is the axis of symmetry, z is the axis with respect to which you apply the moment, and x is your longitudinal axis. Also in this picture, you see that the z-axis is also referred to as neutral axis, or the whole surface here at y0 basically it is referred to as neutral surface. We come to that in a second. So other assumptions that we make is that horizontal lines become curved. So here, if you think of horizontal lines here that are straight, they would become curved here. Vertical lines, they remain straight, but they rotate. So if I want to exaggerate them, they do something like this. The third assumption is that plane cross sections remain planes perpendicular to longitudinal axis. So basically what that means is that if you have a bending, you would always see something like this, that your longitudinal axis remains perpendicular to the planes. You can imagine the direct consequence of this assumption is that basically we are assuming that if we have a bending, we are dealing with an arc of a very large circle. So this is sort of that assumption. But we come to that later again. So just to have all the assumptions that are valid for bending, you see this slide basically. And we also made similar assumptions before when we talked about a torsion problem. So again, this picture shows the bending deformation of the straight member that we talked about. Before the formation, you see that the member is, let's say, straight. And after deformation, when you apply the moment M, it's going to bend. Now, when this thing bends, when the beam bends, what happens is that on the upper surface, you would have a compression. So if you think of, for instance, the last surface on top, or the last line on top, you can imagine that after deformation, after bending, the length of that line is smaller than its original length. So if you assume the original length was L0 here, after bending, you are basically compressing the line which is on top. So the line on top is under compression and its length is smaller than its original length. At the bottom, on the other hand, you can imagine that the line is getting longer, so its final length is larger than its original length. So the line at the bottom is under tension. And obviously, you can imagine that somewhere in between, the length of the line doesn't change, and that is what we call the neutral surface. So on that surface, the bending does not change the length of the surface. So this concept, you can actually try it with a soft material. If you try to bend it, you can see that. So for instance, if you think of a little rubber pipe and you think of these three lines, that they have equal length at the beginning. After you bend this, and I exaggerate it a little, after you bend it, you see the lines, they would deform like this. So when you bend it like that, the outer surface here, it gets longer than it was originally. The inner line, it gets compressed, so it gets smaller than it was originally. And then somewhere in between, you would have that line or that surface where it doesn't change its length, and we call that the neutral axis. Or if we look in the other direction, we call it a neutral surface. All right, so based on the assumptions that we know so far, and based on this picture, what we want to do is to take a little incremental portion of this beam, and for that part we want to analyze the deformation of that, the strain and stress inside that portion, and basically we want to formulate the deformation for that little incremental part, and we go from there. And this process is again very similar to what we had done also for torsion before. All right, so basically what we want to do is to look at a straight member before the formation, take a little incremental piece in that with the length delta x, assuming that we know where the neutral axis is, and then we want to look at that after the formation. So after bending, you can imagine that if you have moments according to our plus direction, our plus convention, the beam will deform like this. And as I mentioned, basically the idea is that every cross section, it remains plane and it remains orthogonal to the lines, meaning that this whole part, it would be an arc of a larger circle. So basically you can imagine that there is a imaginary center for that circle somewhere, and using that, basically you can define an angle delta theta to identify the length of each piece, or each piece of the arc in front of that delta theta angle. So if you look at the first picture, you look at delta x, and you look at delta S, so delta X is the incremental piece or the incremental length on neutral axis. Okay, so this is on neutral axis, and we know on neutral axis before and after deformation the lengths will remain the same. So that's why here you have delta X, but also at the bottom here you have exactly the same delta X, because you know under deformation it's not going to change. But if you think of delta S, after deformation, after bending, you get delta S prime. And then again, delta S prime on top of the neutral axis is smaller than delta S. Below the neutral axis is larger than delta S. And then at the neutral axis, delta S prime and delta S is the same, which is exactly delta X. So now with this insight, what you can do is to look more carefully into this piece, and based on the geometrical features that we have, we can write the equation for strain distribution. So for the little increments here before deformation, if you want to define a strain would be the change of length divided by the original length, and then you take a limit of that when the original length goes to 0. And then again, the piece that we talked about here is exactly what you see here at the bottom, and then the one here is exactly what you see here. So strain is change of length divided by length. In this case, if I want to calculate the strain for the red line here, it would be delta S prime minus delta S, that would be the change of length, divided by delta S, which is the original length, when delta S goes to 0. Now delta S itself, if you remember, delta S is equal delta X. And delta X is not changing due to bending. That would be rho delta theta. So rho is the radius of curvature. Remember that we talked about the imaginary center of that circle. So basically, if you have a bending problem, you can think of a radius of curvature here, rho. And this is basically the distance from the center of that imaginary circle up to neutral axis. So this would be your neutral axis. And therefore, if you have an angle delta theta here, you can write delta X equals rho delta theta, which is equal to delta S. And that's the relation you have here. Now, for delta S prime, it's not on delta X, but you can basically play the same game. So if you think of the distance here, and you multiply that distance by this incremental angle delta theta, you also get delta S prime. So delta S prime is rho minus y times delta theta. Again, remember the distance here is simply rho minus y, because rho is the distance from the center to neutral axis, and then you set your coordinate to measure the distance from the neutral axis. So this would be y, this would be rho, and therefore the distance here is rho minus y. So delta S prime is rho minus y delta theta, And if you insert this into your strain formula, you see strain would be minus y divided by rho, which makes sense because you can imagine that if y is 0, you would be on neutral axis, and on neutral axis you expect the strain to be 0. If y is larger than 0, then you can see that strain is negative, which is compression, and that also makes sense. That's what we discussed about. So above the neutral axis, you expect to see a compression. Below, you expect to see a tension for this type of moment that we apply here. And then if y is less than 0, that is below the neutral axis, then epsilon is larger than 0, which would correspond to a tension, which also makes sense. Okay, so this is what we have so far, and we want to elaborate on that a little more. So based on the analysis we had, now we know strain distribution would be linear. And if you define your maximum strain, epsilon max, as the strain at the point farthest away from the neutral axis, and we call that distance c, then you can write your strain distribution like this. So you can just say epsilon would be a linear function that reaches to epsilon max at distance c. You would have a minus difference in this picture. The reason is that we define epsilon max as the maximum strain in the sense of being an absolute value of a strain. But in this picture, for instance, you can see that that value is a compressive strain, and for that matter, we define a minus there. Now, this relation is a geometrical relation. It has nothing to do with the material response or stress. And if you remember, in torsion, we also had a relation which looked like R divided by C times gamma max. And there, again, this was max strain. But this maximum strain was shear strain. And basically, you could assume also in a torsion problem that shear strain was a linear function which would go to 0 if R was 0. Here we talk about normal strains, not shear strains, and it goes to 0 at the neutral axis, and it can also be negative. So again, there are similarities between bending problem and torsion problem, and there are also differences. So equipped with this picture, what we want to do next is to calculate the so-called Flexure formula. So we want to know what happens to a stress, and from a stress we want to calculate forces, and from forces we want to calculate moment. And if we do that, then basically we have managed to connect moments to deformation. All right, so what we want to do now is to derive the so-called Flexure formula. So based on the analysis that we had so far, we know the strain distribution looks like this. Again, it's a linear distribution, and assuming that the moments are applied according to our convention, we know above the neutral axis you would have a strain that is compressive, and below the neutral axis you would have a tensile strain distribution. And then again, it's in accordance with our plus convention for the moments. Now, from the strain distribution, we can also draw the stress distribution, obviously. So if you have the normal strain distribution and you have this formula, considering that you know stress is E epsilon for linear elasticity, then you know that your stress distribution would also be a linear function. And based on that, you can also define your sigma max as being E times epsilon max, for instance. And then again, now clearly when you look at the stress distribution, you can see that here stress arrows are pushing the cross section and here they are pulling, indicating that here you have tension and here you have compression. Okay, so now that we know the strain distribution, we know the stress distribution, what we want to do is to calculate the location of the neutral axis. So everything that we did so far was based on the assumption that we know where the neutral axis is, and then we measure the distance from the neutral axis. But of course, the main question is, where is the neutral axis itself? So we need to calculate the location of the neutral axis, and in order to do that, we use our equilibrium equation. That's the only equation that actually we have here. And using the equilibrium equation, we will be able to calculate the location of the neutral axis. So basically, the equilibrium equation here tells you that if you integrate all these little compressive stresses and then you get a compressive force, and then if you integrate all these little tensile stresses and then you get a tensile force, of course these two forces, they should be in equilibrium. So the resultant force of the cross section must be zero. And using this constraint, we can define the distance of the neutral axis from, let's say, from the bottom or from the top of the beam. So in summary, this is what we want to do. We know that stress distribution is linear, so a linear distribution is shown here in the picture. And then you know that in every little incremental area here, dA, if you multiply stress by dA, you get dF. But also we know that equilibrium requires that the integral of dF must be 0 over the area. So this is your equilibrium equation. This is the stress distribution. And what you need to do is to insert the stress here into the equilibrium equation and proceed with that. So that's exactly what we do here. We integrate dF over A, and we know this must be 0. Then you replace the stress, sigma, by its value or by its distribution. If you remember, previously we just showed that stress distribution reads this. And then since sigma max and c, they are constant, you take them out of the integral together with the minus sign, and then you would have this. And then again, remember, equilibrium tells you that this must be 0. So we know this whole expression is 0, but we also know that the term, the coefficient you have here is not 0. So from that, you can basically say that the integral here is 0. So what does that mean? That means the first moment of cross-sectional area about neutral axis is 0. In order to better understand this, let's remember the definition of the centroid. If you remember, the definition of the centroid, or the y-coordinate for the centroid, was y bar equals integral of y dA divided by A. Now, if you compare these two, what you will see is that y bar would be 0. So basically, it tells you if you measure the y-coordinate from the neutral axis, y bar must be 0. In other words, it tells you that the neutral axis is also the horizontal centroidal axis for the cross section. So the neutral axis coincides with the centroid. Otherwise, y bar could not be 0. Okay, so from this formula, now we know where the neutral axis is. So you can calculate yda, you set it to 0, and you can calculate the location of the neutral axis or the y, or otherwise you can just say neutral axis is on the centroid of the cross section. So if you have a symmetric cross section like a square or circle, it's exactly the center, as you know. If it is more complex, you can still calculate where the centroid is. So equipped with the relation that we derived for the neutral axis position, now what we want to do next is to calculate the bending moment. So we want to calculate the moment m that will cause the stress distribution shown in the figure. In order to do that, we do exactly as we did before. For example, for a torsion problem, so the moment m is the integral over area of distance times df, and df is sigma dA, and then instead of sigma stress, we use its distribution. Now there is only one difference here. Previously we had a minus for the stress distribution because we wanted to distinguish where the stress is compressive and where it's tensile. But now in this formula, the reason that we have the stress distribution is to calculate the moment according to our sign convention for the internal moment shown on the left. So on the right hand side, if you want to have a counterclockwise moment, which we assume that would be our plus direction, what you would need is exactly a stress that is compressive on top or above the neutral axis and it's tensile below the neutral axis. Now the next thing you want to do is to take out the stress, the maximum stress, and C out of the integral because they are constant, and what you're left with is the integral of y squared dA over the area. We call that moment of inertia I, and by defining the moment of inertia I, then you would have your relation for bending moment m equals maximum stress times I divided by C. Or otherwise, if you reorder the terms, sigma max is m times C divided by moment of inertia I. So in summary, the relationship between the bending moment m and the stress inside the beam is derived as you see here. Once you have the maximum stress, you can clearly also calculate the stress distribution itself following the relation that we had before. So whether you look at the left formula or right formula, either of them we usually call them Flexure formula, and that is the relationship between stress and bending moment. So this slide summarizes everything that we learned so far. We have our Flexure formula. In this formula, sigma max is maximum normal stress that occurs at a point on cross-sectional area farthest away from the neutral axis. And that would be distance C. M in the formula is the resultant internal moment that we have determined from the method of sections, and we have learned how to do that by drawing shear and moment diagrams. The last thing here is I, moment of inertia, for the cross-sectional area about the neutral axis. What we want to do next is to learn how to calculate the moment of inertia I. In order to learn how to compute the moment of inertia I, we do this using two examples for two different cross-sectional area. First, for a circular cross-section. So for a circular cross-section, you would know that the neutral axis is in the middle because it's passing through the centroid. And if you want to calculate the moment of inertia for this cross-section I with respect to the z-axis, that would be integral of y squared dA. Now for the triangle that you see here, you can write the relation between the coordinate y and the coordinate z and the radius r for each point. And if you do that, instead of y, you can write r squared minus z squared. The next step is to split this integral into the two integrals that you see here. And now if you look at these two integrals, the first one is familiar to us. This is exactly the polar moment of inertia J, which we have calculated before when we talked about torsion. So we know already what is the first integral. The second integral is basically the moment of inertia with respect to y as opposed to z. So if you want to calculate the moment of inertia with respect to z-axis, you would have the distance from z-axis, which is y, to the power 2. And basically that means here is the moment of inertia with respect to y-axis because z is the distance from the y-axis. But also you know that due to symmetry, Iy and Iz are equal. And from that you can see that basically 2 times Iz is equal j, and then that means Iz is equal pi over 4 times c to the power 4. So this is how you calculate the moment of inertia for a circular cross-section. Also, you can do the same thing for a rectangular cross-section, and that is what we want to talk about. So if you have a rectangular cross-section with the width b and height h, you know the centroid passes through the center, so we want to calculate the moment of inertia with respect to z-axis. And that would be, again, integral of y squared dA. Now, instead of dA, you can write it as b dy, basically indicating that you are thinking of incremental areas like this. And instead of integral over a, now, because you have dy here, you would integrate from minus h over 2 up to h over 2, which is equal to 2 times the integral from 0 to h over 2. And if you do that, the moment of inertia with respect to z-axis for a rectangular cross-section reads 1 over 12 bh cubed. Okay, so this is the second example. Now, you may have another type of cross-section which is just made of different rectangular cross-sections. If you have something like this, what you would do is that the first thing you need to do is to calculate the neutral axis for the whole cross-section. So assuming that you know where the neutral axis is for the whole cross-section, you would calculate the moment of inertia for each part with respect to its own neutral axis or its own centroid, and then you add them up by considering also the distances that they have with respect to the neutral axis. So what I'm saying here is that basically in this case, for instance, you would assume that you know the neutral axis lies here, assuming that your cross section is made of three parts, 1, 2, and 3, and each of them has area A1, A2, A3, with the distances D1, D2, and D3 from the neutral axis. What you can do is to calculate I bar 1. Now, I bar 1 is the moment of inertia of section 1 with respect to its own neutral axis. So that would be 1 over 12 bh cubed, but then b1 h1. So the dimensions for the cross section 1. And then you can do that for each of them. So you calculate I bar I using 1 over 12 bi hi cubed. And then in order to account for the offset, you would multiply the area of each section times the distance to the power 2. So basically what you would have here is then the moment of inertia for the entire cross section is the sum of this whole expression. And then you would have it a sum over I. Here I goes from 1 to 3. But if you have more cross sections or more parts, you can always use this. So you would have the I bar I, which is again the moment of inertia of each section with respect to its own centroid or its own neutral axis, plus the offset term, which is the area of each part times the offset distance to the power 2. All right, so using what we have learned so far, now we can look into a few exercises together and better learn how to deal with bending problems. Exercise 1 in this lecture is similar to problem 612 on page 294 of the book. The simply supported beam shown in the figure has the cross-sectional area given below. So this is the cross-section. Determine the absolute maximum bending stress in the beam and draw the stress distribution over the cross-section at this location. So similar to before, the first thing we want to do is to draw the free body diagram of the system. And for that, we indicate the reactions from the supports as AY and BY from the supports A and B respectively. Then we can replace the distributed load by its equivalent force. That would be 30 kilonewton downwards. And then for that system, you can write the equilibrium of forces in the y direction and equilibrium of moments with respect to a point, for instance, point A. And if you do that, you get AY equals 15 kilonewton and BY equals 15 kilonewton. Alternatively, you could just imagine that you have a force 30 exactly at the center. It's a symmetric system, so it makes perfect sense that you would have 50 kilonewton on each part to cancel the 30 kilonewton. All right, so once you know the reaction at AY, you can draw the shear force diagram according to what we have learned before. So the shear force starts from 15 then we have a uniform or uniformly distributed load with the slope -5. So all you have to do is to start from 15, you draw a line with the slope -5, and you end up at -15, which is the force at the support B. Okay, so the equation of this line is basically 15 minus 5x, and then again -5 is the slope of the line, which is the uniformly distributed load. Once you have the shear force diagram, from that you can also draw the moment diagram. You know that the moments would be 0 at the two ends, and then because the shear force is a linear function, the moment diagram would be a quadratic function. But also you know that the maximum moment would be 22.5, because delta m would be integral of v dx, and then if you integrate from point A to the center where m is maximum, again m is maximum because we know v is 0, which is m prime. So if you calculate the area of the triangle, you would get 22.5. It's 1/2 of 3 times 15. All right, so once you have the maximum moment, what you need to do next is to calculate the maximum stress. So maximum stress, we use the Flexure formula for that. It's mc divided by I. And m here is the internal moment, or the maximum internal moment in this case, because the question asks us to calculate the stress at the section where we get the maximum moment. So you insert 22.5 in this formula, that's done. But the next thing we need to do is to calculate the moment of inertia I. So the moment of inertia I for the cross section here shown in the figure is composed of 3 parts. And for each part, we can calculate the moment of inertia with respect to its own center line, and then we add the offset term to it according to what we have learned before. So for the base part, for the main part, you would have 1/12 times 0.02 times 0.3 to the power 3. This is exactly the formula 1/12 BH cubed. And then for the two parts on top and the bottom, with respect to the neutral axis, which is at the middle, we will have exactly the same sort of contribution. So we do not need to calculate them separately. We just calculate the same thing and we multiply by a factor of 2. And now if, for instance, if we look at this one, I bar for that section would be also 1/12 BH cubed, which now H would be the thickness of that, which is 20 millimeters. So you would have 0.2 to the power 3. B would be the width of that, which is 250 millimeters. So you would have 0.25. So basically this term is your I bar 1. This is your first term. And then you calculate the area times distance from the neutral axis. Now the distance from the neutral axis is 160 millimeters because you have 150 here and then you have half of 20, which is 10 millimeters within the section itself. So once you do the calculations, you can get the moment of inertia for the total cross section. Next, you just insert this formula, or you insert these values into the Flexure formula. You know already what is the maximum moment. It's 22.5 kilonewton meter. You know already what is I, moment of inertia, it's here. And C is the maximum distance from the neutral axis, which is 170 millimeters. And that is again 150 plus 20. So that would be a point here with maximum distance, or a point here with maximum distance. So once you have that, you know the maximum stress would be 12.7 megapascal. That means on this picture, at the section or at the line farthest away from the neutral axis, you get the stress of 12.7 megapascal. But from that information, because you also know that stress at the neutral axis is 0 and then it's a linear distribution, then you can also draw the stress distribution. And if you do that, you see that, for instance, at point B, right on the corner where the two sections meet, you would have 11.2 megapascal as a stress. And then again, at the center, at the neutral axis, you would have stress 0. Pay attention again here that although we calculate stress as 12.7 megapascal, on top, on the upper part, we have a compressive stress. And at the bottom, you have a tensile stress. So according to what we have learned before, maybe you want to call it minus, and you may want to call this plus. All right, that's it. That's the answer to this exercise. Exercise 2 is similar to problem 613 on page 295 of the book. The beam shown in the figure has the cross-sectional area given. Determine the maximum bending stress that occurs at section AA. So section AA is placed 1 meter away from the support. And at the end, here you have a force applied. It's not a moment anymore, it's a force, and the force is not vertical. It has two components. It has a vertical component and it has a horizontal component. So we are asked to calculate the maximum bending stress that occurs at section AA, and for that we begin with calculating where the neutral axis of the cross section is. So the cross section is composed of 3 parts. You have this part on top, and then you have 2 identical parts on the sides. So what we need to do is to calculate the distance from top to know where the neutral axis lies. The distance y bar. So y bar, if you remember, this is basically the location of the centroid, and we learned that we can calculate that using this formula for cross sections that are composed of multiple parts. And that's exactly what we do. So we have these 2 parts on left and right. For each of them, we know that their centroid is at the distance 100 millimeters from top. So that's your 0.1 here, that's distance from top. The 2 is because you have 2 of them on right and left. And then the term here you see is basically height times thickness. So this is their area. So the first term is for the 2 sections on the sides. And then the second term here is basically the distance of the centroid of this section from top. So the height of that rectangular part is 20 millimeters. So the distance from top would be 10 millimeters. That's this 0.01. And the area is height 0.02 times width 250 millimeters, which is 0.25. So by doing this, you can now calculate the distance of the neutral axis from top, that is y bar, and that would be almost 59 millimeters, which is shown here. So now that you know where the neutral axis is, you need to also calculate the moment at the cross section. And if you like, also the shear force. You need to calculate the moment to compute the stress distribution. And then again, maybe for that, you should remember that the stress formula was mc divided by I. So that's why we need to calculate m to calculate stress. So in order to do that, you write the equilibrium of moments with respect to a point here, for instance, at cross section AA. So you have the moment m in counterclockwise direction. So it's coming with a plus. Then you have the distance 2 meters times the vertical component of the force. That's 2.4 times 2. So 2.4 is the vertical component of the force. 2 meter is the distance. Again, that will also cause a counterclockwise moment. So it comes also with a plus. And then you have the horizontal component of the force, 1 kilonewton, that basically is applied here. So it has a distance from the neutral axis, and because of that vertical distance, you also get a moment due to that horizontal counterparts of the force. So that would be also counterclockwise. So you see a plus sign here times 1, which is the horizontal component, times 59 millimeters, which is the distance from the neutral axis. So doing that, you can see that moment would be minus 4.859 kilonewton meters. Now again, remember the formula that we want to use is sigma max equals mc divided by I. So now we know what is m. Again, we need to calculate the moment of inertia I. And what we want to do is exactly use the same formula as we did before. The cross section is composed of 3 parts. So what you need to do is to sum up the components together, or the moment of inertia of components together with respect to the neutral axis. So here you see the 3 parts. The last 2 are identical because they are for the left and the right parts, and they have the same moment of inertia with respect to the neutral axis. And the first line is the moment of inertia of this part with respect to the neutral axis. So as you can see, again, we follow the formula 1 over 12 bh cubed. For this part, B is 250 millimeters, h is 0.02, and then the area is here times the distance from the neutral axis. So the distance of the neutral axis of the section from the neutral axis of the whole section. So you would have that. And then for each part on the side, you would again have 1 over 12 bh cubed. Now b would be 15 millimeters, h is 200 millimeters. And then you have the area, but here for the distance, this would be the distance of the center or centroid of each of these minus the neutral axis. So that would be in the middle, which is at 100 millimeters. So you need to subtract that from the 59 millimeters and that to the power of 2. So doing all that, if there is no calculation mistakes, the moment of inertia should be 42.26 times 10 to the minus 6 meter to the power 4. All right, long story short, now we have the moment. We have the moment of inertia. All you have to do is to insert this into your formula. Sigma max equals mc divided by I. And now c is the distance from the farthest point. So you can imagine that there is a point here that is fairly far, but then you have another point here that is even farther. So if you call this point P1 and you call this point P2, you can see that P2 is farther from the neutral axis, and the distance of that is 141 millimeters. So you insert that in the formula and you get sigma max equals 16.2 megapascal. So this is the answer, but I just want you to pay attention again that if you want to know whether this is a compressive stress or not, you can now look back at the sign of the moment or the convention that you used here. And from that, you can see that this is actually a compressive stress. Okay, so basically at the bottom half of this picture or below the neutral axis, you would have compressive stress. Above, you would have tensile stress. And then again, this follows from the fact that you have a minus sign for bending moment, although we had assumed it was counterclockwise. All right, so this was our third section on the topic bending, and we discussed sections 6.3 and 6.4 of the chapter 6 of the Hibbeler book. We have in total 4 lectures on the topic bending, so we have 1 lecture more to come. I'll catch you in the next one.